This is the second lecture on numerical methods for conservation laws. And this lecture, we take a look at a few examples that give some background motivation. In particular, there are some unique challenges associated to conservation laws, such as, for example, the emergence of discontinuities or the existence of multiple weak solutions, for which we need, as we shall see later, entropy conditions to single out a unique physical solution. The whole point of this lecture is to provide a few examples that give us some insight into what are the typical challenges in the numerical treatment of conservation laws.
We have previously seen transport equations as very basic but instructive examples for conservation laws. So we have got this PDE given by the time derivative of uxt plus the x derivative of axt times uxt equals 0. In this context, the flux takes the form f of uxt equals axtu, and this function axt is the velocity of the transport phenomenon. One application is modeling traffic flow. Suppose you've got a highway modeled as a one-dimensional line, and let's say the function u represents the traffic density. And let's suppose that all the traffic flows with some velocity given by axt at any position x in time t. So for example, at some times the velocity might be higher, maybe it depends on the time of the day, and it also may vary from position to position. In some segments of the highway, there's a higher velocity than in others. Then the traffic can be modeled by the transport equation. And even though the transport equation may at first glance appear very simple, it already exhibits many important phenomena of conservation laws.
So let's have a look at our old friend, the transport equation, and actually take a look at successively more complicated transport equations. And we begin with a setting where the transport speed is constant. So suppose that A is a constant, and the conservation law of the transport equation now has a very familiar form, namely the time derivative of u plus a times the x derivative of u equals 0. As we shall see, the solution is constant along certain lines known as characteristics. So even though the transport equation arguably is a very simple partial differential equation, it already allows us to introduce a few very important concepts in the study of conservation laws. So in order to get towards characteristics, let's have a look at the formulation of this conservation law. The time derivative plus a times the x derivative equals 0. This can also be understood as a vector product, also known as scalar product or dot product. To consider u as a function in x and t, then the Jacobian is a vector with two components, the x derivative of u and the t derivative of u. That is the Jacobian, just a vector. And what this partial differential equation tells us is that the Jacobian multiplied with a constant vector a and 1, a in the x component and 1 in the t component, that this dot product equals 0. The partial derivative of the function u in x and t in space-time direction a1 equals 0. Now, of course, it just means that the function must be constant along that space-time direction. And that leads us now to the introduction of characteristics. So we know that the solution must be constant in that direction. So in particular, if we introduce some initial values at time t equals 0, then we can already completely characterize what the solution u looks like at all times. If we consider the function u naught x, which shall be our initial values at time t equals 0, then we get uxt equals u naught x minus at as a form of the solution. From any space-time position xt, we just travel back along the characteristics until we get to time t equals 0, and there we can read off the value of the function u.
The transport equation with constant velocity has a solution that is easy to describe. Starting with the differential of a function, the graph of the function shifts in the direction of the velocity. In this case, we've started with a sine-shaped function, and according to the velocity parameter a equal 1, it shifts in the positive direction.
No PDE is too simple as to not introduce a few interesting concepts. The transport equation with constant speed is a very nice preparation to the transport equation with varying speed. And here we shall already see that the concepts that we have introduced still apply, but in a slightly more complicated form. So again, we take a look at transport equations, but this time we suppose that ax is a differentiable function in x. So we assume that the speed depends on the position x as well. One application of that, if you want, is a very simple model for traffic flow. Suppose you've got cars on a highway, and you take a look at the density of the cars along the highway. In certain areas, there might be a different speed than in other areas, and that can be modeled by the transport equation with spatially varying speed. If we have got the transport equation, this variable speed, if we plug this in to the basic form of the conservation law, then we easily see that the PDE can be rewritten as follows. We've got the time derivative of u plus the x derivative of a times u plus a times the x derivative of u equals 0. So we've just used the product rule. And in order to apply the method of characteristics, first we rewrite this. The time derivative of u plus a times the x derivative of u equals negative the x derivative of a times u. So in particular, what we see from there is that in direction ax1, the derivative of u equals the negative x derivative of a times u.
The underlying idea of characteristics is that we can rewrite the partial differential equation as a family of ordinary differential equations. For that purpose, we need to identify curves along which the partial differential equation looks like an ordinary differential equation. And the very first step in this context here is, of course, to identify the curves in the first place. So suppose we have got some initial values u0 at time t equals 0. We want to follow the characteristic curves and solve the corresponding ordinary differential equations along them. The characteristics themselves are defined by ordinary differential equations. Namely, we have that the t derivative of the position x of t shall equal a times x of t, and x0 shall equal x0, where x0 is some initial position at time t equals 0. For every initial position x0, we have got such a characteristic equation, and provided we can solve this ordinary differential equation in x, we have a full description of all the characteristic curves. In particular, if the velocity a is always positive or negative, then the characteristics do not intersect. This is going to be part of the homework, in fact. The solution theory for these characteristic curves, of course, depends to some extent on the velocity a. In most cases, we can apply the solution theory of ordinary differential equations, but we do not follow this into much more detail now at this point. So let's suppose we've got such a curve, then we can revisit our calculations before, and we consider u along such a curve. So let's take a look at the value of u along this characteristic curve, which is given by u xt at time t, and given that expression u at x of t and t, we take the time derivative. The time derivative using the chain rule evolves as follows. The x derivative of u at xt at t times the time derivative of x of t plus the time derivative of u at x of t, t. That is the first equation. The second equation now just uses that the time derivative of x of t equals the velocity at x of t. So we just substitute a of x of t. But just a few minutes ago, we have seen that that expression can also be written as the negative x derivative of a at x of t times u of x of t and t. And notice that, again, u of x of t and t is just the value of u along the characteristic curve at time t. That leads us now to an ordinary differential equation. For every characteristic x of t, we only need to solve the ordinary differential equation time derivative of v of t equals negative x derivative of a at x of t times v of t, with initial value v0 equal u naught at x of t, u naught at x naught. So if for every initial position x naught, we calculate the characteristic curve and then solve the corresponding characteristic ODE along that curve, which gives us v, then v always represents the value of u along that curve at time t. Now, if we read off u at the characteristic curves, the hope, of course, is that from those characteristic curves, we can get the solution for the original partial differential equation. This technique of characteristic curves is a very popular one in the theory of partial differential equations. And of course, the hope is that once we've solved the characteristic ODEs, that we can obtain, in the end, the solution for our original PDE that we're actually interested in. For example, that can be achieved if the characteristic curves cover the entirety of spacetime. However, later on, we shall see that this is not necessarily the case, and even worse, sometimes also the characteristics are going to intersect.
Let us visualize the transport equation with variable velocity. The initial data are a shifted sine function, again, here in blue, and the other plotted line denotes the velocity. As you can tell, in the middle of the interval, the velocity is rather low, whereas at the boundary points, the velocity is higher. As the traffic, so to speak, moves into the middle of the interval, we enter a low speed zone. Correspondingly, a bulge evolves and proceeds with low velocity. But then, as the barge enters the higher speed zone, the barge quickly deflates. As the content quickly rushes over this speed segment, it enters the low speed zone once more, and another bulge evolves. This simple example illustrates an important phenomenon. If the flux not only depends on u, but also on x, then the values along the characteristics may change. For example, we see that the bulge achieves a much higher amplitude than the initial values. That is fairly typical to the case where the flux depends on the spatial variable. We've seen that the transport equation exhibits a few phenomena that look very similar to waves. And this is even more true of our next example, namely Burger's equation. Burger's equation is another PDE, that is a conservation law, and it reads as follows. The time derivative of u plus 2 times u times the x derivative of u equals 0. We recognize that PDE as a conservation law. The flux is given by f of u equals u squared. So in particular, we can also write this as the time derivative of u plus the x derivative of u squared equals 0. The background of Burger's equation is, on the one hand, just being an important model problem for numerical methods for conservation laws. If we want to test a numerical method, then Burger's equation is a model problem. And if the method fails for that model problem, then probably it's not going to work for anything more complicated. That being said, Burger's equation can also be considered as a very simplified model in fluid dynamics. So very specifically, the background of Burger's equation in fluid dynamics is as follows. Consider the one-dimensional Navier-Stokes equation with incompressible fluid, no external force, constant pressure, and constant density. That equation reads time derivative of u plus 2 times u times x derivative of u equals v times delta u. In this partial differential equation, u is the velocity of the fluid, delta is the Laplacian, and v is the so-called viscosity. In such a setting in fluid dynamics, if the viscosity v is negligible, meaning that v is much smaller than 1, then approximately the behavior of the fluid is described by the time derivative of u plus 2 times u times the x derivative of u.
being roughly equal 0. In other words, we get Burger's equation. So you might say that Burger's equation describes waves in a one-dimensional fluid. In particular, as we shall see, the velocity of the waves is proportional to the density of the fluid at this point. You could also say that higher waves travel with higher velocity. Let's have a look at the characteristic curves of Burger's equation. So if you write this equation in the form time derivative of u plus 2 times u times x derivative of u equals 0, then we already see that the solution u must be constant along the lines in direction 2u, 1. We go 2 times u steps in the x direction and 1 step in the time direction. So in principle, finding the solution should be easy. It sounds a bit similar to the transport equation. Given x naught and the initial value u naught x naught at the initial time, the solution will be constant along the curves x of t equal x naught plus 2 times u naught x naught times t. Along those curves, the solution will always have the value u naught x naught. So how difficult could it be? Burger's equation already shows one of the most fundamental problems in the discussion of conservation laws, namely the emergence of discontinuities. And for the sake of demonstration, let's suppose I have Burger's equation over the unit interval from 0 to 1, and let's say we impose periodic boundary conditions. We could start with smooth initial data. For example, u naught of x could equal the sine of 2 pi x. We can start writing down the characteristics, just taking a look at the original conservation law. And then we see that the speed of the characteristics is proportional to the value of u. In particular, the characteristics start intersecting right after the beginning of the evolution. Even starting with smooth initial data, the characteristics start to intersect. One could say that we have got two waves in this setting. On the left, we've got a positive wave moving to the right, and on the right, we've got a negative wave moving to the left. And of course, they start crashing into each other. This can be modeled by a discontinuity at x equal 1/2. To make this discussion a bit more vivid, let's have a look at a numerical simulation. As we let this example for Burger's equation evolve, we have two waves crashing into each other. The positive one is moving to the right, and the negative one is moving to the left, just like the characteristics predict. And as the two waves crash into each other, a discontinuity appears. When the characteristics of the values 1 and -1 touch, then this gap, this discontinuity, has the largest extent, and from now on, it only diminishes over time. The shock in the middle has been placed at x equal 1/2. But in fact, it was somewhat an arbitrary choice. What exactly tells me that the shock curve does not take another trajectory as time evolves? For example, we could have a shock curve that starts at t equal 1/2 and then moves on further to the left. So what is the natural criterion to actually choose a shock curve that is physically admissible? Actually, this phenomenon is quite catastrophic, because on the one hand, u should be the solution of partial differential equations. So in particular, it should already have derivatives in the x and time direction. But as we see here, in this example, even if we start smooth initial data, we may run into the situation where discontinuities evolve immediately. So in particular, the solution of the partial differential equation is not even differentiable. That indicates that we are going to need a new sense of solution, a generalized sense of solution. We've seen that Burger's equation tends to evolve discontinuities out of nothing, that we need a new sense of generalized solution for conservation laws. But let's finish the discussion with a somewhat more positive note. Namely, we can also recover a conserved quantity. So suppose that we've got an interval from 0 to 1, again with periodic boundary conditions. And let's have a look at the solution of Burger's equation. What we can tell is that the solution will have constant integral. If we take the look at the time derivative of the integral from 0 to 1 of u, then of course, first we can pull in the time derivative into the integral, and then we can use the conservation law. So this equals the integral from 0 to 1 of the x derivative of u square. But now, because we have periodic boundary conditions, that equals u1 square minus u0 square, which equals 0. So we can tell from the conservation law that the time derivative of u remains constant over time. So let's summarize this lecture. What we've seen is that even smooth initial data may lead to discontinuities because their characteristics intersect. That's a new mathematical challenge for conservation laws and will also be a challenge in their numerical analysis. What we've not yet discussed is that sometimes the characteristics do not cover all of space-time, which means the method of characteristics does not provide the entire solution. That means we will need a technique to fill in the empty space-time, so to speak. The solutions themselves are often not differentiable, which means in particular we need a new sense of solution. And we have also seen that the evolution of the characteristics is not time reversible. Over time, information is lost. In particular, the time evolution cannot be reversed. But we've also encountered already one conserved quantity. And that is also quite characteristic for conservation laws. Given appropriate boundary conditions, we can see, for example, that the integral of u is conserved. And similar phenomena can also be proved for other conservation laws and systems of conservation laws. So much for now. Until next time.